different, they are on the opposite side of your carbon-carbon double bond, we tell them as trans. But in these cases, suppose you just consider this example. Here it is, there is no similarity among this bromine chlorine or fluorine CH3. So in this case, it is difficult to actually assign cis and trans, cis and trans. So in this case, what we will do, there would be rather instead of cis and trans, there comes your E and Z nomenclature. So whatever would be your Z configuration when you have the same priority group on the same side. Like low priority, we will come, where comes the priority? Low priority on the same side, then that would be Z. And when they are on opposite sides, that would be your E configuration. For example, in this case, that 1 bromo, 2 chloro, 2 fluoro, 1 iodoethane. In this case, if you just see, in this case, on this side, on this carbon, this one is your priority, it would be priority number 1, and this one would be your priority number 2. So in this case, we have to give priority individually to the carbons in your double bond. So on this left carbon, iodine and bromine, iodine is of high priority and bromine is of low priority, and on the right side carbon, chlorine is of high priority and fluorine is of low priority. So high priority are on the same side, so this is a Z configuration. So there is one rule, that is your Cannon-Gold-Prelog rule, in which your each carbon, these two substituents are ranked according to the atomic number of the atom. Whatever with the atomic number, higher atomic number would get the first priority. And the other one would be the lower priority. Then the same would be applicable for the other carbon which is present on the other side of the thing. If the same on the same side, the ranked one or priority one are on the same side of the top pi bond, then that is given the descriptor Z, and if it is on the opposite side, then it is given E. For example, in this case, in this example, if we see on this carbon, we have bromine and fluorine. Bromine is having higher atomic number as compared to fluorine. So bromine is priority 1 and fluorine is priority 2. And on this carbon, our chlorine is having more priority as compared to CH3. So here both the same priority are on the same side. So this is going to be your G. Okay. And this one is going to be your E. Similarly, what we will do here, okay, here we have on this side, this carbon, one side is bromine, other side is carbon. So we don't have any problem giving the priority to this one. But on this side, both are attached to carbon, then we have to consider the second point of attachment, then the third point of attachment. Here the second point of attachment is again carbon. Here the second point of attachment is carbon. But in this case, the third point of attachment is carbon, but in this case it is OH. So this is going to be priority number 1 and this is going to be priority number 2. So this is again Z. So this is about how we assign E and G notation in case of your geometrical isomers. Similarly, in the last class, we have discussed about the configurational notations for your optical isomers. So in optical isomers are those which can rotate the plane polarized light. So there you have two enantiomers. If one enantiomer rotate the plane polarized light to clockwise direction, the other enantiomer, that is its mirror image, will rotate the plane polarized light in anti-clockwise direction. So here the nomenclature, there are two types of nomenclature. One is your relative nomenclature, which we have discussed in the last class also. So in case of relative configuration, that is your DL system of nomenclature, this glyceraldehyde is taken as your standard. So in that case, when the OH group, here in L-glyceraldehyde, the OH group is on the left side, and the right D-glyceraldehyde, the OH group is on the right hand side. So whenever there is any other molecule where your same type of group which is similar to your OH or more electronegative element that is present on the left hand side, that will be given the denotation as L, and whenever that more electronegative group, or the group like OH group, would be on the right hand side. That would be given D notation. For example, in case of our sugar molecules, in case of sugar molecules, only the lower chiral carbon is taken into account. So the OH group is on the right hand side. So this is denoted as D. And in case of our amino acids, the NH, here we have a NH3 group. So this NH3 group is similar to your OH group. So this is present in your left side. So that is denoted as L-alanine. So RH system of nomenclature also we have done, that is your absolute, and mostly we use it in your IPS nomenclature. So in that case, you have to check, you have to first give the priority, or rank the atoms according to their atomic number. Then you just see the fourth priority is away from the viewer, or it is towards the viewer. If it is away from the viewer, you don't have to worry. Then you just rank it, and when you trace the path from 1 to 2 to 3, if it is clockwise, then give R, and if it is anti-clockwise, then give it S. But if it is not in your the ranked 4 is not in your away from the position, but it is towards you, in that case you have to just take the opposite. First you just trace the path from 1 to 2 to 3. If it is giving you your counterclockwise, then it should be S. But as the CH3 group, the lower priority group, is not away from the observer, rather it is towards the observer, so its actual configuration would be just opposite to it. So therefore the chiral center, in that case, it would give you R. Similar is the case whenever you have it in your Fisher projection formula. So if the lower priority group is on the vertical side, so whatever be the configuration, it would be the same. But if it is on the horizontal side, so if it gives R, then you have to just change it to S. So vertically good means we just say it is when it is vertically clockwise R, anti-clockwise S. But whenever it is not in a vertical position, rather the lower priority group is in the horizontal position, then you have to just reverse the result. So this is the another example. We will not go in detail. We have already discussed in the last class. So next is how we determine the configuration. This is just we are we are given the structure, and we are just assessing like what is the absolute configuration. But how we know the configuration from your chemical methods or in any method. Suppose we are getting a compound, we do not know what is its configuration. So in that case, there are different methods. Two methods are there in your syllabus. One is your determination of configuration by chemical correlation. So in this method, it involves a chemical transformation of a compound uh, whose configuration we do not know. So we just transform it to another compound in which configuration we know. And you have to do it in such a way that the bonds linked to the stereocenter or asymmetric centers are not affected, and the stereochemical outcome of the reaction is already clearly known. For example, if we just take glyceraldehyde, okay, in glyceraldehyde this carbon number 2, that is a chiral center, but we do not know the exact configuration of it, whether the H is on the right side or OH on the left side. So glyceraldehyde can be converted to your tartaric acid. For example, when glyceraldehyde is treated with HCN, hydrogen cyanide, so now this CHO group that would undergo nucleophilic addition reaction, now here this you just see the shaded area that remains constant. Okay, so now that gives you a by different mm, another two steps, that gives you your tartaric acid. Okay, these are the three tartaric acid that is known. One is your minus tartaric acid, plus tartaric acid, and mesotartaric acid. Actually, diglyceraldehyde, when it is converted to tartaric acid, it mostly gives you tartaric acid 1 and tartaric acid 3. These two have this configuration. You just see the shaded uh, carbon where the configuration is written. So here the hydrogen is on the left side and OH is on the right hand side. So that means the glyceraldehyde, because this center is not changed, that does not take part in your reaction. So that means it should be already there in your diglyceraldehyde. So in that way, the the configuration of diglyceraldehyde can be proved. That means the OH is on the right hand side and hydrogen is on the left hand side. In this transformation, as you can see, this carbon number 2, that does not go on any change, only we have done the reaction here. Okay, so that means whatever be the configuration of tartaric acid in this carbon, that should come from your diglyceraldehyde. So from this you can find out the configuration of your glyceraldehyde at carbon number 2. Similarly, another example, suppose we have your serine. We do not know the configuration around this carbon, but whenever it is treated with phosphorus pentachloride, this CS, uh, here there would be nucleophilic substitution. Again, you just do the amination. Okay, and this amine, diamine, can be can be found from an amide. Okay, can be found from an amide by your Hofmann degradation. In any of this transformation, you just see this carbon does, um, there is no change in around this carbon number 2, and this amide again can be hydrolyzed to give you asparic acid, where its configuration is known, where the NH2 group is on your right hand side and hydrogen is on your left hand side. So from this you can just conclude that the D-serine has NH2 group on your left right hand side and hydrogen is on, means the serine has NH2 on the right hand side and hydrogen on the left hand side. So that gives us a D-serine. Another method is your quasi-racemate. We know that racemate or racemic mixture obtains when we have suppose here I have D-serine. If I just its enantiomer or its mirror image would be your this sorry, its mirror image would be NH2 on the NH2 on your left hand side and hydrogen on your right hand side. So it would be the mirror image of your D-serine. So whenever we have the exactly 50-50 mixture of this one would rotate the plane, if it rotate the plane polarized light in clockwise direction, this will rotate the plane polarized light in anti-clockwise direction. So whenever you have a 50-50 mixture of both, 50-50 mixture of both, then the plane polarized, there would be no rotation in plane polarized light, because the first it would be clockwise, then again anti-clockwise, so the net rotation would be 0. So that mixture, whenever you have both the enantiomers of the compound in equal amount, then that mixture is known as your racemic mixture. So there is another one that is known as your method of quasi-racemates. So here we said these are racemates, because in racemic mixture we have both the enantiomers, they are known as your racemates. So what about this quasi-racemates? So the quasi-racemate is a co-crystal of two similar, they are not same, they are similar but distinct compounds, one of which is left-handed and the other one is right-handed. They are not same compound, means they are not enantiomers. Okay, although chemically different, they are sterically similar. Okay, what is the similarity between them? They are sterically similar. We would just consider this one. You just see, this one is our 2 chloro 1 2 3 4. Okay, or this is your chlorosuccinic acid and this one is your bromosuccinic acid. Okay, they both are, if you just see here, the chlorine is up down the plane and bromine is here up the plane. Okay, these two are not enantiomers, they are not of the same compound, they are not the enantiomer of same compound, but these two, when you just mix these two, they form a racemic, they form a racemate. Okay, so this is known as your quasi-racemate. They are not actually racemate, but they are more or less equal to your racemate. So they have an almost mirror image relationship. Just You see, if we just change these two groups, okay, and we have these two groups are different. Such compounds are later called quasi-enantiomers. So these are quasi-enantiomers. So if we have 51:1 mixture of quasi-enantiomer, that forms a quasi-racemate. Okay. So how we will determine the conformation configuration of any unknown compound by this method? So if A and B, okay, here if we just say chlorosuccinic acid and your bromosuccinic acid, this is plus chlorosuccinic acid and this one is your minus bromosuccinic acid. So suppose this is your A and this is your B. Okay, so if we just form these two, mix these two, that forms a quasi-racemate. Okay, so how we know that is forming a quasi-racemate? So if that form a quasi-racemate, then that forms a we will go through it. If you do the 1:1, if that forms a compound, that forms a compound, we tell them as quasi-racemate. How we know that that will form a compound? Just a minute. Okay, if these two form a compound, how we will know that that will form a compound? If we just study the phase diagram. Okay, if we study the phase diagram, that is their melting points. So here you see this is the melting point of 100% A and this is the melting point of 100% B. If they form a compound, then their phase diagram would be like this. If we just go on decreasing the percentage of A and go on increasing the percent of A, then that it gives you, here we have a 50% racemate. So if it forms a compound, so that would give you a phase diagram like this. And if does not form a compound, it forms simply a solution, that would give, so this is for compound and this is for the simple mixture. Okay, so if they form a compound, so that means A and B are quasi-racemate. If they form a compound, so this is a quasi-racemate. If they do not form a compound, they would give like this type of curve, then they are not forming a quasi-racemate. Or we would just say if A and B form a compound and A and the enantiomer of B, if A and B are forming compounds, and if we just take A and instead of minus bromosuccinic acid, if we just say take the plus bromosuccinic acid, so that gives us a mixture or a solution. Okay, so from that we now know the configuration of B. From that we can find out the configuration of A, because that would be the opposite configuration. If they form the mixture, then A and B should be of same configuration. As you see here, A and B are forming a quasi-racemate. A is of plus and B is of minus. But if they are not forming a compound, if they are forming a mixture, they would have the same configuration. So from this, you can find out the configuration of your unknown compound by forming this quasi-racemate with a compound which configuration we know it. So that is the method of quasi-racemate. Next comes your stereogenic and prochiral centers. Okay, so what is your stereogenic center and a prochiral center? For example, if we just see this compound, that is your aldehyde, this is not chiral, but by doing only one transformation, this is a nucleophilic addition reaction. By doing only one transformation, that gives us a chiral molecule. So this carbon here is known as your prochiral center. And when that gives a chiral compound, that's carbon center. For the time being, I will say that that is a stereogenic center, or we just say at your chiral center. Okay. So prochiral center, which gives you a chiral compound or a stereogenic center after one single transformation. If two such chemical transformations are required, that is also known as your prochiral center. Here we just need one transformation to get a stereogenic center. If we need two transformations, two such chemical transformation, then that center is called as your prochiral center. Even in this example also, you see, if we exchange this hydrogen, with deuterium, that also gives you a stereogenic center, because this is not chiral, you have two hydrogens here. So that's why this carbon is your prochiral center and this is your new stereogenic center. Next comes your topicity and flow stereoisomerism. These terminologies we should actually know before going in detail. So, what do you mean by topicity? Okay, before that, suppose you just consider this molecule. In this molecule, we have two hydrogen atoms. Okay, we will say that these are two hydrogen atoms. They look similar to us. Okay, thus we just tell them as your homomorphic. Okay, those are apparently identical. Thus such ligands when considered in isolation have same form and are indistinguishable. But such ligands are distinguishable when present as a part of a molecule. For example, you just take this one. In this case, uh, both these hydrogens are homomorphic, because if I just replace it, any of this hydrogen, if I replace it with bromine, suppose this one CH3, I replace this hydrogen with bromine, it would give me hydrogen, this 2 bromo propane, or if I just remove it with this hydrogen, that would also give me 2 bromopropane, and these two are not your stereoids, they are the same. Okay, because we have, this is not a chiral molecule, that is not going to give us a chiral molecule. You see, we have the same type of groups on both the sides. So this propane or this dichloromethane, this two hydrogen atoms are known to be homotopic, or we can just say these hydrogens are homomorphic. Okay, but if you just consider these two hydrogens in case of your bromochloromethane, so if we replace this hydrogen 1 by fluorine, that would give us this compound, and if we replace this hydrogen by fluorine, that is going to give you this compound. If you just see, these two are just mirror image of each other and they are not superimposable, they are going to give you enantiomers. That means these two hydrogens are different, so that is known as enantiotopic hydrogens, and just in general we will tell them as they are heterotopic. Okay, they are heterotopic because they are giving you two different molecules. Okay, two different isomers, stereoisomers, and as these stereoisomers are enantiomers, so these hydrogens we would tell them at your enantiotopic. So homomorphic, homotopic, and heterotopic. Again heterotopic, here we get your enantiotopic. Suppose we have a chiral center already in this carbon number 2. Just take this molecule. Here we have mm, 4 carbons. So carbon number 2 is already chiral. So now we have two hydrogens in carbon number 3, H1 and H2. Okay, if we replace hydrogen number 1 by chlorine, that is going to give us this compound, and if we replace hydrogen number 2 by this chlorine, that is going to give us this. So if you just see, these two are not mirror images. You see, this is not a mirror image. Here you have the mirror image relationship, but here you do not have mirror relationship, because you, this chiral center is not going to change. Okay, so that means they are not mirror images, but they are the stereoisomers, so these are known as your diastereomers. So in this case, these two hydrogens are heterotopic, but as that is giving you diastereomers, we can say them as your diastereotopic. From this we can just say, like homomorphic ligands, again homomorphic ligands can be homotopic and heterotopic, again heterotopic can be enantiotopic and diastereotopic. Similarly, the phases can be, as here we have this ligands, we can have homotopic phases as well as your heterotopic phases. Suppose in this case, in your formaldehyde, when we do the Grignard reagent, attack it from the, whether the Grignard reagent is going to attack from the top, it is going to the same alcohol in both the cases. But in other than your aldehyde, if we are going to attack your Grignard reagent, that will give us two alcohols which are exactly which are the mirror image of each other. So that we can just say that it would be your enantiotopic phases. So how we give the names to these prochiral centers, or how we this uh, prochiral centers of these heterotopic ligands, how we give them the names. Suppose the first example where we have your bromochloromethane. So these two hydrogens, when hydrogen number 1 is replaced, that gives us this compound, and hydrogen 2 is replaced, that gives us to this compound. So if we check the stereo, which if we check the absolute configuration in this case, your bromine is of first priority, chlorine is of priority number 2. Okay, this one is priority number 3 and priority number 4. And this priority number 4 is on your horizontal axis. And if we go from 1 to 2 to 3, that gives us your S. But as 4 is on your horizontal axis, so that should be your R. And in this case, again 1, 2, 3, and that gives you clockwise, but hydrogen is again on your horizontal axis, so that would be your S. Or you can do the rotation like this, and to bring your hydrogen on your vertical axis, then you can get your configuration. Or you just do that easy method. Okay, so now by the replacement of this hydrogen 1, we are getting R configuration. So that's why this hydrogen 1, we just say that is your pro R, because that is going to give us the R enantiomer, and this hydrogen 2 is going to give us your S enantiomer, so that is known as your pro S. So similarly, we have stereo heterotopic phases. That means if we going to R react, these are, we have two phases here, up and your down. So the nucleophile can attack from up phase or your down phase, top phase or your down phase. So similarly, the up phase is known as your re. So how we do that? If we trace, while we observe from the up phase, we trace from 1 to 2 to 3. If it goes in clockwise direction, then that would be re phase. And when we hear the it is given, if we see it from below the face, okay, from the in that phase, and if it traces the path anti-clockwise direction, then that is known as your C phase, Si. Okay, so if you just see, if the ethyl group is going to attack from your top page, in case of your Grignard reagent, then OH will come here, and pH is already up, so ethyl would be here and OH. So that gives you R. And if it is going to attack from bottom phase, that is going to give you S. Next is stereogenicity. Okay, so where we say the stereogenic center. So a stereocenter is an atom of a group of atoms if the interchange of two ligands attached to it results in a new stereoisomer. As the stereoisomerism is generated by such a center, it is called stereogenic center. So stereo center got a when we interchange two ligands, it gives you a new stereoisomer. Whether it is enantiomer or diastereomer, that doesn't matter, but it gives you a new stereoisomer when you interchange two ligands. For example, in this one, we have 1, 2, 3, 4. If we interchange the ligands between 1 and 2, okay, 1 has taken the place of 2 and 2 has taken, we just interchange ligands 1 and 2. So if you just see, these two are enantiomers. I can just write the Fisher projection, okay, 1 and 2, and 3, 4 like this. So you just see these two are enantiomers. You just see this is, we can just rotate it, okay, we can just rotate it, so that that would be your, we can do two more, sorry. So two more swaps, so that one would be go up and two would be down, and this would be 3 4. So this is the mirror image of this one. So these two give you enantiomer. So in that case, this carbon is known as your stereogenic centers. For example, if we just check this mesotartaric acid, we interchange the ligands as this position. Okay, so at C3. So when we interchange the ligands at C3, that means H will come left and OH will go right hand sides. So in that case, these are not enantiomers. That gives a different diastereomer, but still that is a stereogenic center. They are not enantiomer, but that gives you a diastereomer. So these two are known as your this carbon is a stereogenic center. Okay, even if we exchange the ligand at carbon number 2 in this case, okay, that is going to give you another diastereomer. These two are not related by mirror image. They are not mirror image of each other. So these are your, that gives another diastereomer, but still carbon number 2 and 3 are your stereogenic center. Suppose in this case, in your cis-2-butene, if I interchange carbon this CH3 group and hydrogen, then we get a trans-2-butene. So that means you have a chiral stereogenic axis here. That gives a different isomer. Next comes another terminology, chirotopicity. So chirotopicity is the phenomenon related to presence of a chirotopic atom. A chirotopic atom is an atom which resides in a chiral environment. This concept involves a local or site symmetry within a molecule. So within a chiral molecule, all points are chiral. So for example, we would check whether some molecules have your chirotopicity or not. For example, in this mesotartaric acid, we know that this is not a chiral molecule because we have a plane of symmetry. So that is a meso compound. Okay, the upper half is exactly the mirror image of your lower half. So this is, you have a plane of symmetry. So we would check whether we have a chirotopic atom in this case or not. Whenever we have a chiral molecule, all the points are chiral. We do not have to check chirotopicity there. But in case of some achiral molecules, we would see whether this has a chirotopicity or not. So if you would just see this one, these two carbons, they are chirotopic in nature because they remain in an chiral environment. We would see in other examples also. First of all, this example, as you see this molecule that is chiral. So all the points in this should be chirotopic. Let's explore the stereogenicity at carbon number 3. Okay, so if we change, we know that stereogenicity, if we interchange the groups, it should give us a different stereoisomer. Then that would be your stereogenic center. So here, as this molecule is chiral, all the points are chirotopic. So here, if we just interchange the ligands or the groups at carbon number 3, we are going to get this molecule. And we will see whether this one is the same as this one, or this one is different, or this one is a diastereomer, or enantiomer of the first one. So if we just do a 180-degree rotation, okay, if we do a 180-degree rotation, COH group would come here, the carbon number 1 would come here, and carbon number 5 would go up. So if you just see, the this molecule and this molecule are remaining the same. That means carbon number 3 is not a stereogenic center, but this is a chirotopic. This point, this carbon number 3 is not a stereogenic center, but it is chirotopic. And another, just check this nivaric acid, or like your mesotartaric acid. In mesotartaric acid, we do not have this carbon number 3, but here we have carbon number, and the plane of symmetry is right through your carbon number 3. So the upper half is exactly the mirror image of your lower half. So this is a this is a meso compound. So we will see this carbon number 3 is chirotopic or not. Okay, but as this molecule is not chiral, we would just check again and again check whether carbon number 3 is stereogenic or not. So if we interchange the OH groups and hydrogens at carbon number 3, we would see that they give different compounds. They are giving you your diastereomers. If you rotate it, that is not going to give you the same compound. So this carbon number 3, as this is not a chiral compound, that it gives you a keratopik but stereogenic center. Carbon number 3 is having a stereogenic center. Although the molecule is not chiral, but still we are having a stereogenic center. So now this one, here we have 4 different groups attached to it. Okay, so the carbon number 3 has H and OH, and we have 2 groups in blue and pink colored. If you can just see, you will say that these two are the same. They look the same. So that means this carbon number 3, and they are same in constitution. They look same, but do they have the same configuration? Just check. Okay, so now this carbon number 3, in this one, carbon number 3, we have H, OH, and the upper one is having a configuration of R, and the lower one is having a configuration of S, just by putting your this one. And the other one from which we have started, the OH group is on the right hand side and H is on the left hand, and this is R and S. So now while giving the CIP rule, so this is given first priority, this is your second, and this is your third. So whenever giving priority to your configurations, R always precedes over S. So that gives you 1 2 2 2 3. So uh, that would give you a re. There is written, or small r, I think small r. It would be as it is counterclockwise, but hydrogen is on your horizontal axis. So that would be r, and this would be given s. So this type of symmetry, or this type of asymmetric center, is known as your pseudoasymmetry. So when your tetrahedral carbon is attached to 4 different groups where 2 of them are configurationally different, rather they are same, they are constitutionally same, but the 2 of them are configurationally different, one is R and another is S, such a center is called your pseudoasymmetric center, and this phenomenon is known as your pseudoasymmetry. Next, how we induce asymmetric in any reaction or in in any molecule. So before going to that, we should know there are some selectivity or specificity in organic chemistry reaction. First is your chemoselectivity. So whenever you have 2 different type of functional groups, one functional group is reacting faster, or selectively one functional group reacts. So for example, whenever you use your Lindlar catalyst that primarily target your alkene, uh, okay, uh, adds to alkene as compared to in your alkynes. Okay, and regioselectivity, such as in case of Markovnikov addition, whenever you have there, you get 2 compounds, one is your major, another one your minor. Okay, so you are getting 2 constitutional isomer, one major over the another. And in case of stereoselectivity, one stereoisomer is formed in excess as compared to your other enantiomer. For example, in this surface epoxidation, you are getting one major enantiomer, the other enantiomer is formed in your minor one. So you have chemoselectivity, regioselectivity, and enantioselectivity. Regioselectivity means H is going to add on this carbon or this carbon. So in that way, you are getting 2 different constitutional isomers. Next is another one is this stereoselective. This can be enantioselective or your diastereoselective, and again it can be selective or specific. Okay, for example, in this case, in this elimination reaction, you can get E alkene or Z alkene. So in this case, you have a choice of 2, but one is major, one is minor, but that is going to give you stereoisomers. So that is your stereo selective. But if we just see Uh, in this elimination reaction, okay, in this elimination reaction we do not have any choice, and here some bulkier base if you take, bulkier base if you take, then in that case only this hydrogen will be removed and you are going to get only one stereoisomer. So in that case, that is known as your specific stereospecific. This one would give only this isomer only. So that would be your stereospecific. For example, our SN2 reactions, your in case of your SN2, okay, this one. And in case of your SN2 reaction, if you take R, that is going to give you S only, the product, or if you take your S alkyl halide, that is going to give you R only. So that means space that is specific to your reactant. So this one will go is going to give only this specific compound. But in case of your SN1 reaction, that gives you a racemic product, that is going to give you a mixture of both. So that gives a racemic mixture. So that is not a very good stereochemical. It does not have any stereochemical preference in SN1. But SN2 reaction is stereospecific because only one particular enantiomer or any particular, we know that this substrate is going to give this one only. So that is very specific. For example, halogenation of alkene is also stereospecific. So that is going to, cis butene is going to give you a racemic mixture of S. We know that it is specific. It is not going to give any other compound. Even cis would give you a mixture of S, S and R, but trans is going to give you a meso compound, that is S and R. So this cis would never give this one, or trans would never give this one. So that is specific to your reactant, to your starting material. So that reaction is known as your stereospecific. Again, diastereoselective. So diastereoselective means, so that is going to give you two diastereomers. One is formed preferentially as compared to the other diastereomer. For example, in case of your epoxidation reactions, one is going to give you a major product and this is going to give you a minor product, and these two are not mirror images because already a chiral center is there. So this which are fixed, so that means only the configuration here is changed. So this is not a mirror, these two are not mirror images, so they are diastereomers, and as one is formed in excess as compared to the other, so this is the diastereoselective reaction. So asymmetric induction, some rules are there. While doing some reactions, there are some rules. So first rule is your uh, Cram's Prelox and Felkin ion model. So according to this model, uh, I would first one is your Cram's rule. I just wrote something here. Okay, no problem. So in case of your Cram's rule, in the nucleophilic, so this rule is this Cram's, Prelox, and Felkin's rule that is being used for the nucleophilic addition reactions of ketones only. Okay, so in that case, your that is viewed in a Newman projection formula. So according to Cram's, what you do, like you keep the uh, uh, ketone, that is the carbon oxygen double bond, the carbonyl group just towards your, that is in the front carbon, and the large group should be positioned just opposite to it, and then the attacking nucleophile would prefer to come for addition to the carbon atom from the side of the small group. So it has a chance to attack from this side or this side, but it will attack from your side of your small group, because here whenever nucleophile is attacking here, it would experience less steric hindrance as compared to whenever you have a medium sized group. S stands for small sized group, M stands for your medium sized group, and large sized group is opposite to your carbonyl oxygen. So in that case, here, then when the nucleophile now can attack from both the sides, from this side or from this side, so this attack is is more preferable as compared to this attack, because here it would experience more steric hindrance as compared to this one. So the major product would be a result of nucleophilic addition, nucleophilic attack from the site where your small group is present. For example, in this case, this molecule. So in this case, your C6H5 is your large group and CH3 is your medium group and this is your small group. Okay, this is we are talking about the first carbon, the alpha carbon to your carbonyl group. Okay, whenever your nucleophile, in this case our nucleophile is your C6H5 MgBr. So this is a Grignard reagent, as we know this would be negative charge, Mg plus this is plus. So the nucleophile C6H5 minus, so first you have to give it in a Newman projection formula in which your this one is the front carbon, this one. So we have put it carbonyl there, hydrogen here, and this large group that is your C6H5 just opposite to it. And here this one is presented in such a way that we are formed it in a eclipsed conformation. In case of your crumbs rule, the conformation or the rule is prepared in such a way that the eclipsed conformation has taken into account. So now the nucleophile has two sides. It would attack from where your hydrogen is there and where your CH3 group is there. As hydrogen is of a very small size, nucleophile will prefer to attack from this one. So that would give you a product like so now as we have HCH3 and C6H5 already there. And now as the nucleophile attacks from there, so we have a nucleophile here and OH group here and hydrogen will come here. Or from this you can just see the C6H5 attacks from your opposite side, so that goes just CH3 is on the top phase here, so it attacks from the opposite side or the side from hydrogen, so it would have the same side of hydrogen, so that gives you this compound as your major product, not as your this one. This gives the 3O. 3O means both the hydrogens on the same side and erythro on the opposite side. So that the major product is from the nucleophilic attack from the same side of your smaller group. For example, in case of lithium aluminum hydride reduction, as you can just see here, the small, this is your large group, this is your medium group, and this is your small group. So the product which is formed, that is here, the addition would be your hydride. Hydride will be attacked here. So in that case, if hydride attack from the side where your hydrogen is there, then that is also going down the plane. So this is going to be your major product and this is going to be your minor product. So next is your Felkin model. So Felkin just what he did, he just improvised that Cramps model in which he said that okay, your large group has not to be just your opposite to your carbonyl oxygen carbonyl group, but it has to be in a perpendicular way. So like this, in this case he has formed this taken this Newman projection in a staggered conformation. And here also, like you see, this is the carbon. Suppose we have a like this, and we have a large group, we have a medium group, and we have a small group. So the nucleophile first, you have to write down the projection. So in that case, the carbonyl oxygen and your carbonyl oxygen and the large group on the second carbon are in perpendicular direction. Okay, and the medium and small groups are present here. And here also the nucleophile has to attack from the side of your smaller group side. Okay, so now the nucleophile will attack from, there are two sides, either it would attack from this side or it would attack from your this side. So it would be better to attack from your smaller side, that would, which would give you the major product. There is another extension of your Cramps rule in which here also, that is mostly in case of your alpha ketoester, whenever one nucleophile is attacked to in this carbonyl carbon that is your alpha carbonyl carbon of your alpha keto ester. In that case, the nucleophile attacks from the side where your small group is present. So now if your nucleophile is attacking from the side where your small group is present, from this you can just see the small group is off the plane. That means the R dash would attack from off the plane only. So if it is going to off the plane, that means it is end of will your configuration where R dash group is off the plane or the solid wedge structure. So most important is whenever there is a nucleophilic addition reaction, whether it is Cramp's rule, Prelog's rule, or Falken's rule, so everywhere the nucleophile will attack the carbonyl carbon from your small side, the small group present in your uh, adjacent carbon, not from on the side where your large group is present. Okay, I think we should take a break, 5 minutes break here. Then we can just rejoin in 5 minutes. Is it okay? If we just take a 5 minutes break?
Yes, ma'am.
Okay. We will join by 7:35. Okay.
Okay.
Okay, we will start now. So, are you all back from the break? So, should I start now?
Yes, ma'am.
Okay. Okay, so now we have just discussed that in the nucleophilic addition, in case of your carbonyl compound, that the nucleophile will add to the carbonyl carbon in such a way that it has to overcome, or it has to be in the site where you have a small ligand attached to the substrate. If there is any steric hindrance in your substrate already present, then it will give you the compound, or the nucleophile will attack in such a way that it would come from the direction where you have your small ligand or group attached to it. So next is your how conformers or configurational isomers are going to give you different reactions, and they react how they react. Okay, first of all, whenever we have a substrate or reactants, there we can have conformationally rigid diastereomers, or conformationally mobile diastereomers, or substrates with two or more conformers. Okay, first we will discuss what are your conformationally rigid diastereomers. That means these diastereomers cannot be interconverted. For example, in this cis isomer, oh sorry, I have not done in the slideshow mode. Okay, so this two isomers, that is your one, two, three, four. Okay, four tertiary butyl uh, hexanol, cyclohexanol. In that case, these two diastereomers, they are conformationally rigid. That means you cannot interconvert them, because this tertiary butyl group is always fixed in your equatorial position, and they are trans, and the OH group is always on trans. So this is not going to interchange to its axial isomer, because this one, as this is, you are having equatorial position, the tertiary butyl group and OH group is also in your equatorial position, so that is not going to transform to its conformational other conformation. So this is a very rigid diastereomer. These two are diastereomers, and even this cis isomer, where OH group and your tertiary butyl group are cis to each other, this always, the equilibrium is always onto this side, not to the other isomer. So these two diastereomers are very rigid. Even this trans 2 decalol and trans 2 beta decalol, they are not going to, as we know that trans decalin does not undergo flipping, because trans decalin is being formed by the means fuse of your equatorial bonds. So in that case, these two are also very rigid diastereomers. Then you have conformationally mobile diastereomers. In that case, if you just see, these two are your diastereomers, and these two give different. They are mobile. You can this hydrogen. This they will react, but these two will react differently to give you different products. For example, your 3O isomer and erythroisomer. 3O is going to give you tetralone, in which that was giving you a six-membered ring. Okay, that involves the, in case of 3O, it involves the cyclization of COOH group and this carbon here. Okay, so that gives you a six-membered ring, and in this case, inverse the cyclization here with your benzene ring here, the benzene here. But in case of erythro, you do not have a C6. In case of your erythro, it does not go there. Rather, it forms a compound here that forms a five-membered ring here. So they two are your diastereomers give different products. So whenever you have substrates with two or more conformers, okay, for that thing, for some substrate, the overall reaction rate depends upon the specific reaction rates of the conformers and the ground state population of the conformer. In the ground state, we can have different conformers. So kindly mute yourself. Okay.
Sorry, ma'am. Sorry.
Yeah, yeah, no. Uh, so suppose we have two or more conformers. Okay, in the ground state, some conformers would be more stable, so its population may be more, and some would have less population. So the overall specific reaction rate depends on the specific reaction rate of your conformer. Suppose we have two different conformers, conformer A and conformer B, and its reaction rate is suppose Ka and its reaction rate is Kb, and in the ground state we have Na number of this and we have Nb number of this. Then the overall specific reaction rate would be the summation of both this, a summation of Ni Ki. So this equation is applicable when interconversion of conformer is much faster than the reaction. That means one conformer is going to another conformer. That means your cyclic one in your chair conformation, as we know that it can flip equatorial to axial, it can go. Interconversion is much faster than your reaction. Suppose we are doing the reaction, A is going to give rise to product C and B is going to give rise to product D. But these two are interconversion is faster. So in that case, the conformers could be homomeric. That means they behave identically with respect to the rate of reaction and product formed. That would going to give the same product. Enantiomeric behave identically under achiral conditions, means whenever you are not giving any chiral condition, they are behaving same but differently under chiral conditions. And diastereomeric, that they behave different ways. For example, uh, take the example of your malic acid. Okay, so this malic acid, it has two conformers. Just if we see, these two are the same malic acid. Just here, the this one is, these two are on the same side. Just you have just rotated on this plane so that COH has, means it has been rotated once only. Okay, so H2 has come to H1 and COH go to this. So these two are different conformers. Okay, these two conformers, but when done the dehydrogenation, so in this conformation, this hydrogen is anti-periplanar to this OH group, that gives rise to your malic acid, in which both the COH group are on the same side. But in this conformation, your this hydrogen 2 is opposite to your OH group, so in that case that gives you fumaric acid, uh, which is a trans, is this is your cis, that gives you trans. That means from the same malic acid which is present as a two conformers, these two are the conformers. In your reaction mixture you have two conformers, so one is going to give you malic acid and one is giving you fumaric acid. So these two are your diastereomers. Okay, so how these are related and which one is going to give you more product, that is being governed by one principle, that is your Cotton Hammett principle. So which correlates the product distribution with the transition state energies. What is this transition state? In the next class, I will go with it. But whenever we do a reaction from reactant, we go to a product. So that involves a lots of bond breaking, and so that path from going reactant to product, it must pass through a energy maxima. So that is known as your transition state. It is not, it just passes through that energy maxima. So that is known as your transition state. So the more this energy, the reaction rate will be slower. The less this transition state energy, that would be slower, and the rate of reaction would be faster. So this Curtin-Hammett principle correlates the product distribution with the transition state free energies formed by the two conformers. Mm, this rate equations correlates the overall specific reaction rate of the given substrate with the specific reaction rate of the individual conformer. For example, we have these two are our conformers A and B. This substrate has two conformers A and B, which can be interconverted by an equilibrium constant K1 and K2. Okay, so the product, and A conformer gives product C and B conformer gives product D. The product composition is not in direct proportion to the relative concentration of starting conformation of A and B. How much product will be formed, that does not depend on the relative concentration, but it depends only on the difference in free energies of the transition state. For example, if we just see, this is our conformer A and this is our conformer B. Okay, so from going from A to B, that also needs one transition energy, and from A to C, that goes through a transition energy, and from B to D also, that goes through a transition energy. So that the rate of reaction, the product composition formed, the that depends on the difference in free energies of the transition state. So we can just write the overall reactant constant is equal to K1 by K2. The product ratio will not depend upon the concentration ratio of the starting conformers, but on the difference in your, this one is your del G. Del G is your change in free energy. That is the difference between free energies of del G C and del G D of the transition states. That is your change in free energy. So there are four conditions. More stable conformer giving the measure product. Okay, which one is your more stable conformer that gives you the measure product, provided the rate of reaction of more stable conformation is higher. For example, in this case we have, this one is your A conformer A and this one is your conformer B. So conformer A is of less energy as compared to conformer A, so this is the more stable conformer, and conformer A gives you product C and conformer B gives you product D. As you see, conformer A to C requires less energy as compared to your B to D. So the measure product would be from your conformer A. So more stable conformer giving the measure product, provided the rate of reaction of more stable conformation is higher. For example, in this two, uh, here we have a butyl bromide to cis 2 butene formation or trans 2 butene formation. So in this case, uh, it can have two different uh, conformations. Okay, so in which, in one, your CH3 groups are just close to each other, or these two are your uh, opposite to each other. So it is not exactly the C, because here you would have gauge interaction. So this one is less stable, this one is more stable, so B should be more stable. But again, uh, uh, this is the basic idea, that whenever you have a more stable conformer, that gives the measure product, provided the rate of reaction of more stable conformation is higher. And the second one is less stable conformer giving the measure product, which one is your, for example, in this case, here among A and B is your less stable, but still that would give you the measure product, because its rate of reaction to D, that is here the energy is less as compared to you this one. So in that case, the measure product would be formed by your conformer B. So that would give you more measured product. For example, in this case, it is the more stable conformer, but its its product formation to give you this one is uh, this one is less, this one is slow. So that may but here we have a less stable conformer, but its reaction is very fast. So in that case, the major product would be this one, because the rate of reaction of this less stable conformer is faster as compared to the rate of reaction of your more stable conformer. And in another case where both the conformers are of equal stability, of equal energy, so in that case the product is formed in which your rate of reaction is less. For example, in this case B to D, here the energy required is less as compared to this one. So the major product would be from B to D. So for example, in our transform, uh, trans that is your di-equatorial, and this one is your trans diaxial. These two can be in the room temperature, they interconvert easily. So in case of trans di-equatorial, that this geometry is not appropriate to undergo your um, beta elimination. In case of diaxial, that does not undergo beta elimination. Rather, in case of your trans diaxial form, that is in the appropriate geometry to undergo beta elimination to form your epoxide. So this diaxial form, in this case, this is of less energy, this conversion is of less energy, and this conversion is of high energy. So that means from this enantiomer we get the from this conformer, not enantiomer, from this conformer we get the measure product. For example, another example is here where we have two conformers. In this case, we have two enantiomers actually. These two enantiomers, because this is up the plane, this is down the plane, and this is the stereogenic center. And these two enantiomers can be interconverted just in the presence of an acid or in the presence of an base. So that is, it's this one is the intermediate state. So it can go from 2 to 4 uh, by passing through 3. So in this case, if enantiomer 2, in case of enantiomer 2 and in case of enantiomer 4, when enantiomer 2 is get hydrogenated, we are getting this antiproduct. Okay, they are opposite to each other. This is up the plane and this is down the plane, and if this one is going, they are going to give you the syn product. So in that case, in both the cases, this one is very fast to give you anti-product, and in this case that is going to be your syn product, which is not observed. So that passes through a less energy, sorry, from this one, from less energy as compared to here, which passes through a higher energy. So the major product comes from conformer number 2, not from conformer number 4. So in this kind of reaction, if you have a mixture of both 2 and 4, so mostly 2 will give you 1. So to maintain the equilibrium, more and more 4 will be interconverted to 2. So the major product would be your the product which is formed from conformer enantiomer number 2. Next comes our molecular dissymmetry and chirooptical properties. How these properties, how these molecules, these chiral molecules behave in our optical, like we have already discussed that they rotate the plane polarized light. So we will discuss those properties, how this molecular dissymmetry is related to your chirooptical properties. Okay, whenever we see tell about any um, light, okay, so it has both the uh, both the magnitude, both the components. It has an electric component as well as a magnetic component. They propagate along the same direction, but they propagate in your mutually perpendicular direction. So this is just only one type of one wave. If one wave is propagating, it will propagate like this. So if two waves are exactly at the same place at the same time, Okay, so now we can just say this is, if this is your electric waves, these are your magnetic waves. So they would oscillate like this. Okay, so when the two waves exist in the same region of space but have different directions. Okay, so one is going like this, and another one was is a bit different direction. It is going with a bit different directions. So their addition will give different orientations. So next is, suppose these two waves in different directions, but one is moving ahead of another. One is going fast, the other one is going a bit slow. So if this would be like that, then we would have this type of magnetic vectors or electric vectors. So when we have continuously rotate, okay, so not only in one direction, it is going to be in different directions. Okay, we have now many waves. So in that case, it is continuously rotating, so that is giving rise to a circularly polarized light. So circularly polarized light is when a light in which the electromagnetic wave continuously rotate in the same direction is called your circularly polarized light. Now, the circularly polarized light can be of clockwise direction, or it can be of your anti-clockwise direction. Or it can be your right polarized it can be going like this, or it can be going in the other direction. So it can be a circularly polarized light, and the other one is called as your left circularly polarized light. So circular birefringence is, suppose we have we take this linearly polarized light and we pass it through a disymmetric medium such as calcite. Calcite is nothing but your calcium carbonate. So it has two components. It is your left circularly polarized light and the right circularly polarized light. So now they will exhibit the left circular, if it is passing through a symmetric molecule, they won't um, there won't be any difference. They will have the same refractive index. But if it is passing through a dissymmetric molecule, then in that case, your left circularly polarized light and right circularly polarized light would exhibit two different refractive index. Suppose NL is your refractive index for your left circularly polarized light, and NR is known as your refractive index of your uh, uh, right polarized light, circularly polarized light. So this phenomenon is known as your birefringence. Okay, suppose if your right circularly polarized light refractive index is less than the refractive index of left circularly polarized light. In that case, your right circularly polarized light will travel faster in chiral medium than your left circularly polarized light. Okay, if in that case the material is called your dextrorotatory, is known as your dextrorotatory. That means uh, uh, it rotate a plane polarized light in clockwise direction. Okay, if NR is less than NL, that is the refractive index of your right circularly polarized light is less as compared to the refractive index of your left circularly polarized light. In that case, the left circularly polarized light will travel faster in that medium, and in that case, it would be known as your levorotatory. And we can also observe the, in case of a linearly polarized light, you can observe the optical rotation as a function of wavelength, then that is known as your optical rotatory dispersion, ORD-CD. Okay, we know that enantiomers or that rotate the plane polarized light. So if it has a specific rotation, okay, in case of CD or circular dichroism, we just check the rotation at a particular wavelength. But when we check the optical rotation as a function of your wavelength in different wavelengths, then that gives you a spectroscopy, that is your optical rotatory dispersion spectroscopy. We'll come to it. And circular dichroism, what is circular dichroism? Unlike your optical rotation, circular dichroism only occurs at wavelengths of light that can be observed by a chiral molecule. So only at a single wavelength we just observe it. And at this in case of your chiral compound, left and right circular polarized light will be observed to different extents. So when circular dichroism is measured as a function of wavelength, then that is known as your CD spectroscopy. Suppose in this case, when we do not have a chiral environment, in that case, our right circularly polarized light and left circularly polarized light, they are of equal length. So that is observed in equal magnitude. So that gives you a linearly polarized light, because one is left, another is right. But when it is observed unequally, the right would be observed more and the left would be observed less. In that case, that observe a actually elliptical path, so that gives you an elliptically polarized light. In this case, that goes through a circular path, so that result in a linearly polarized light when both the magnitudes are same. But if any of the circularly polarized light, as in this case your right circularly polarized light is observed more, so its magnitude is less as compared to your left, so in that case this goes in a elliptical manner. So in case of your optical rotatory dispersion, in that case, this is the instrumentation for ORD, how this optical rotatory dispersion is being done. So from the, this is the source of the light. Uh, you have a monochromator, then comes your polarizer, which polarizes the plane polarized light to only a single plane, and then it passed through the sample with concentration C. It has a path length L, and it rotates the plane polarized light by some value, that is your alpha, and here you have your analyzer. So this is means at a particular time it will monochromator means it will allow only one a light of only single wavelength. So with you can just take a vary the wavelength and check the optical rotation. So these ORD curves are obtained when we uh, ob- plot a graph between optical rotation of the same sample with wavelength. So each time you just change the wavelength, and if with the decrease in wavelength, that optical rotation goes off, that is known as your positive ORD curve. And with decrease in wavelength, if the optical rotation decreases, then that is known as your negative ORD curve. So there is another effect, so that this happens when you don't have a chiral environment. But when you have a chiral environment or chiral molecule, in that case, uh, here you don't see any maxima or minima. This is a straight curves. uh, that's why this is known as your plain ORD curves. But when you have a chiral compound, so in that case, uh, you get a maximum and a minimum. Okay, so in case of uh, in any compound, if with the decrease in wavelength, uh, it first goes through a maximum, then it goes through a minimum, then that effect is known to be your positive cotton effect. But in case of your where with the decrease in wavelength, I'm saying decrease in wavelength here also, it is written decreasing in wavelength. When we are going from in this direction, this is increasing in wavelength, this is pi, notates your rotation, optical rotation. Okay, so when your while you decrease your wavelength, first it passes through a minimum, then it goes through a maximum. Okay, so in that case, that is known as your negative cotton effect curve. Or you can just say if peak is observed first, then that is your positive cotton effect, and if trough is observed first, then that is your negative cotton effect. Then based on this negative Cotton effect and positive Cotton effect, there are some alpha axial haloketone rule or helical rule. So there are some rules are there to denote your configuration or conformation to substituents. Suppose in this axial haloketone rule, this is mostly for your cyclohexane, where you have a uh, halogen group alpha to it, and that alpha halogen group is present in your axial position. So to give the like whether to give the exact confirmation of this one, okay, axial haloketone rule. So according to this rule, when you look your uh, this molecule from this side, that is head of the from the head of your uh, chair conformation, then if the halogen group, axial halogen group, is present at your right hand side. So suppose you just see here, it is, if we see from this side, this halogen is on the right hand side, then that is going to give you a positive Cotton effect. So its enantiomer, if you just see, its mirror image would be this one, and just you have to uh, so its mirror image would be this one only. So this mirror image, so that means if this one is giving you this one, its mirror image should give you a negative Cotton effect. For example, if we just see it from this side, then this alpha halogen appear to be on the left side of this one, so that is going to give you a strong negative Cotton effect. So according to this axial haloketone rule, when you view a axial cyclohexanone along the carbonyl group, if the halogen, axial halogen, is present on the right hand side, then that is going to give you a positive Cotton effect. And if it is going to give you a it is on the left side, that would going to give you a negative Cotton effect, or vice versa. If you are going to get a positive Cotton effect, then you do not know whether the axial hydrogen is present here or it is in this conformation. So in that case, yeah, if it is giving you a positive Cotton effect, then the conformation should be or this one, or if it is giving you a negative Cotton effect, then this one should be the conformation. So for example, in this case, in this trans 2 decalone, okay, these two are mirror image of each other. So one, if it is giving you positive Cotton effect, for example, this S enantiomer is giving you positive Cotton effect, that means which one should be the enantiomer? So as it is giving you positive Cotton effect, the halogen should be on the right. So this one should be the, if you are viewing along this direction, so the bromine is on the right hand side, so that is giving you positive Cotton effect. Whereas its other enantiomer, if you view it from this side, so this halogen, alpha halogen, is on the left hand side, so that gives you a negative Cotton effect. So next comes your octant rule. So octant rule, suppose we have a, this is a space, okay. So if we just put one uh, uh, one plane here, so in that case I can do it in this way or this way or this way. So that would be give you me space, the space would be halved in this way. So that gives us two quadrants. One is your front quadrant, and the other one would be your rear quadrant, or in total we would get an octant. Okay, so this one would be your front octant, this one would be your rear octant. So how this is uh, visualized, actually in case of one carbonyl, so you just see in this in plane, okay, this space around your carbonyl cyclohexanol can be divided into three planes, mutually perpendicular planes. So that, as it is three mutually perpendicular planes, that is going to give you an octant. And these octants are given like this, the minus plus plus minus. So this is your front octant, this uh, this is your back octant or rear octant. So as you can see from this figure, your carbonyl group, okay, this carbon and carbonyl group, that comes in your front octant, and this these ones comes in your rear octant. Okay, so these octants has signs plus or minus. Okay, whenever you have a substituent or any group in your octant, that gives a contribution to your Cotton effect. If that substituent or group is present in the minus, wherever you have a minus of the octant, if it is present in that one, that is going to give you a negative Cotton effect. And whenever you the group is in your positive octant, then that is going to give you a positive Cotton effect. And whenever it has a substituent on or near nodes that make no or small contribution. For example, if this is carbon number 1, this is your carbon number 4, that is present in a node here. So that any substituent on that one, it does not make any contribution. Okay, so according to this rule, the space, I'm just reading it again. The space around the carbonyl group is divided into 8 sectors called octants by drawing 3 planes as we have done here. The rear sector signs contribute more to contributed. So these rules are used for cyclohexanon moiety. So contribution, there are some mm, rules. Okay, so some assumptions are there. Contributions from hydrogens are not normally taken into account. The fourth carbon atom lies on the YZ nodal plane. So as you see here, so it is on the YZ nodal plane. So that also do not contribute. The substituents present at equatorial positions at C2 and C6 are near the XY nodal plane. Hence, equatorial substituents present at C2 and C6 positions are very small contributions. But whenever it is axial positions, have strong contribution towards your Cotton effect. For example, these two are plus methyl cyclohexanone. We know that exhibit a positive Cotton effect. So among this, you can have this conformation, or this one would be the actual structure preferred conformation of our methyl cyclohexanone, and it gives you a positive Cotton effect. So we will see from these two. Okay, so when we are just viewing it from this direction, so if it is your carbon number 1, this is 2, 3, 4, 5, and 6. So carbon number 1, here we just put it as oxygen here, and on the left hand side we have 2 and 3. So this is 2 and 3. This is your, then here you have 4, this is 5, this is 6, and again in 3 you have a plus here in your equatorial position. As you can see, that is in your equatorial position. So to know that in this quadrant, whenever you have these groups like this, so this is your equatorial, equatorial goes there, axial comes there, equatorial goes there, axial comes here, and equatorial goes there, axial comes here, like that. So here equatorial goes in this direction, and we do not have any other configuration. But when we see it from this direction, okay, when we see it from this direction, so this is our carbon number 1, and this is your 2, this is 3, 4, 5, 6, and here carbon number 2 is on the right hand side, 2, 3. Okay, here the 3 is the substituent is on axial position. This one is your 4, this one is 5, this one is 6. So as you see, in this case, the CS3 group is on positive quadrant. That means this one is going to give you a positive Cotton effect, and in this case, the CS3 group is in your negative quadrant. So that is going to give you a negative Cotton effect. As our compound, okay, that gives a positive Cotton effect, and that means this one should be the preferred conformation where CH3 group is present in your equatorial position, not this one. Okay, similarly, another one example here, if you just see, these two are actually mirror images. It is being written like this, but these two are enantiomers, and this one gives you a positive Cotton effect. If you deduce the structure as it is giving you positive Cotton effect, it can have the structure like this or like this. So if you deduce the structure in this case, it is carbon number 2, we just put this as your carbon number 2 here, and 3 is on the right. 3 is attached to 4, 4 is attached to 10, 10 is attached to 9, 9 is again either attached to 1, and here it is 8, and so on. It is like this. Okay, so in that case your group B is in your positive quadrant, so that's why that gives you positive Cotton effect. But in this case, if you just see here, the this is carbon number 2, 1. So here, as we are viewing it from not in the head, actually this is the tail, so that would be the reverse. So if it is on the right hand side, then it we have to, okay, 2 3, okay, take it. Okay, so 1 is on the left hand side, right hand side, 1 is attached to 9. Actually this one should be viewed on the different direction. Anyway, it is viewed, the figure is given like this. So this is 2, and 1 is on the right hand side, and 3 is on the left hand side. So we can just see that this group, this moiety, the next carbon, the ring B is present in the negative quadrant. So this one would give you negative Cotton effect. As this compound gives a positive Cotton effect, so the conformation should be this one. Next one is helicin. In the last class, we have considered about what is hexical chirality. We have discussed about central chirality, or chirality, having chiral center, axial chirality, planar chirality, and helicins. So helicins also exhibit the helicin rule. So this, how to name this helicity rule, and here we know there is one rule, that is your helicins with p helicity shows positive rotation and positive Cotton effect. On the other hand, helicins with M helicity exhibit negative rotation and show a negative Cotton effect. So, which one is, means P would give you positive Cotton effect and M would give you negative Cotton effect. So, first, how these helicins are named. And so as you can see, this is named as your hexahelicin. It is your M hexahelicin. This is your P hexahelicins. So actually, to give descriptor, stereochemical descriptor for helical chirality, actually I just looked it in Google and got this one. So for first one, for step one, you have to identify the axis of the helix. So this is the axis of the helix. Then you just see which one is your front, or which ring is front to it. All the time the ring which is front, or in case of our chiral carbon, we just give a solid wedge which to that group which is front, or towards the viewer. So you start from there and you just see in the helicins how the rings are going. If you start from here, you just see the rings are going in anti-clockwise direction. If it is going in anti-clockwise direction, then that is going to be M. If it is going through your clockwise direction, suppose this is our front carbon, front ring. So when we go from this to this or the other rings, then that path traces the path in a clockwise direction. That's why that is P. And in this case, this is the front carbon, front ring, and when we trace from the front carbon, front ring to other rings, that traces a path in your anti-clockwise direction. So this is your, if it is clockwise, then that is going to give you P hexahelicin, and if it is in your anti-clockwise direction, that is going to give you, if it is anti-clockwise, that is going to give you M helicin. And again, if P helicin always gives you a positive Cotton effect, and M helicin, its other enantiomer, that would give you a negative Cotton effect. Or positive rotation, rotate the plane polarized light in a positive direction, that would rotate the plane polarized light in opposite direction. Next is, in the last class we have discussed also about your chiral allenes, where we have a axial chiral axis. Okay, so this we have already discussed that allenes, or in case of your parents, here you have chiral axis. So in that case, we have just done the nomenclature. In that case, you can view from both the sides and do the nomenclature. So if we look from this side, so here we have a chiral axis. So when you look from this side, okay, chlorine appears on top, and hydrogen appears on down. So you in the vertical line you just put chlorine on top and hydrogen on down. And on the rear carbon, so this is your front carbon, this one is your rear carbon, and on the rear carbon you have hydrogen on left and CH3 on right. And whenever you do the nomenclature, you have to give it the first ones always precedes the rear carbon. So in that case, this one is priority number 1, this one is priority number 2, and this one would be your priority number 3, this one would be your priority number 4. So 1, 2, and 3. Okay, 1, 2, 3, 4. So while tracing the path from 1 to 2 to 3, then that is giving you S configuration. So this one is your S. And you can also look it from this side. This is another molecule. When you look from this side, so whenever you are putting, always this solid wedge and this dash wedge has to come in your horizontal line, and this has to come in your vertical line. Okay, so when this one is, you are looking from this side, if you just see CH3, when you look from this side, CH3 is on the left side and hydrogen is on the right hand side, and chlorine is on the again top and bromine is down. And here this one has to be priority 1 because we are viewing from this side. So this is your near view, this is your rear view, and near view always gets precedent as compared to your rear view. So this is 1, 2, this is would be your 3 and 4 because bromine is more atomic mass as compared to fluorine. So in that case, when we trace the path from 1 to 2 to 3, that is a clockwise direction. So this is your R configuration. So what about this lowest rule, and how it is connected to the Cotton effect or optical rotation? So according to this, actually I didn't get a vector picture. Okay, so according to this, first you have to write down the projection. Okay, in this case, just check this molecule. Okay, so in this case, uh, here if we view it from this side, okay, if we view it from this side, so in that case, phenyl is on top, or we just put it A and this image B. Okay, phenyl is on top and hydrogen is on down, and this hydrogen, or that is your D, on left, and this one would be of more priority as compared to hydrogen. So this one is C, this one is D, or 1, 2, 3, 4. So in that case, uh, as we go from the path followed, that is from A to B to C, that is anti-clockwise, so this one should be S. The configuration should be S. But what about the Cotton curve? So according to this one, the Cotton curve, the group or the moiety which is present on the vertical line, the first priority group, and the which one is your horizontal line. We already always put this one in your horizontal line, and we put this in your no, so we put this in your vertical line and we put this on your horizontal line. So the first priority of this and the first priority of this. And so if they both are, if they are on the right hand side, then that would be your, give you positive Cotton effect. If they are on the left hand side, they would give you negative Cotton effect. For example, in this one, okay, so you view from this side. So if you view from this side, so this one, we know that this one would always come in your horizontal line. Okay, so this one is your comes horizontal line, hydrogen would be on the left and COH would be on the right, and this COH would be on top and this hydrogen would be on right. As these are your we are viewing from this is the near end, so this is 1, this is 2, this is your 3, and this is your 4. And the connection between this is, this one is the bond in your vertical axis, this one is the higher priority on your, or polarizability, these are known as your polarizability. Okay, this one is your higher polarizability in your vertical line, and this one is of higher polarizability in your horizontal line. And they are, this one is, this is your A first polarity to third polarity, polarizability. It traces a path in your that is towards left, so that is going to give you a negative Cotton effect. For example, in the previous example, we can just see here. So here This is of your first priority and this is of your third priority, and it is on the right side of this one. So that is going to give you a positive cotton effect. And in this case, the first priority and the third priority, from the first priority the third priority is also is towards your uh, right. Okay, that is also going to give you a plus positive cotton effect. But if it is on the left, like or anti-clockwise, oh, okay, this case, oh, sorry. So this is going to give you negative cotton effect, as the case is here. When you go from first priority to this priority, that is going in a, okay, I am a bit confused here. Yeah. So that is going in an anti-clockwise manner, then that is going to give you a negative cotton effect. For example, if you just consider any other examples, you can just see. So just one thing, if your first priority, from first priority to your third priority, if it is in a clockwise direction, that is going to give you positive cotton effect, or if it is in the anti-clockwise fashion, that is going to give you a negative cotton effect. So I hope you understand it. You have to do a lots of actually practice to come to understand these things. If anyone is having any doubts, we can just discuss. So today we discussed about how we actually determine the configurations, and also among two conformations, which one is the actual conformation from the optical data. Also we discussed about your how to assign notations in your helicins, and also how they are going to give you whether it is how they would behave in an optical activity, or how they are going to give you circular dichroism, how that curve will be given. Or also we discussed about all those specificity on how asymmetric can be induced in a molecule by reaction, and how we can find out the configuration by chemical means or by quasi-racy means. So if anyone is having any doubt, you can just ask me. I will try. So you can just go through NPTEL lectures also. They have actually this axial halogetal rule, or this Kram-Spirlog's rule, or octant rule. The NPTEL videos are very good actually. You can just go through those. The NPTEL videos by, you can just put asymmetric induction or axial halogeton rule, and NPTEL lectures. Some IIT Kharagpur professor, some Basak. His lectures are very. I found that very interesting actually. He has done in detail, uh, so you can just watch all those videos that is available in YouTube also. So you can just Google search in Google that NPTEL lectures on your axial halogetal rule or disymmetry. He has done a lots of modules are there. So you can just take your relevance, whatever is relevant to you, but almost is covered there actually in that modules. All your these things are, so you can just go through those. uh, so if anyone is having any doubt, we can discuss. Otherwise I will just sign out.
Good night, ma'am.
Do you have any doubt, service?
No, ma'am.
Okay, okay. Okay, you just practice, and tomorrow also we are having class. Tomorrow and day after tomorrow, I have two more classes, and actually there are. This is a huge course to cover into four classes. That is in 8 hours. So, but you have to practice a lot and go through YouTube videos. I hope. Okay. So,
Okay, ma'am. Okay.
yeah, that's all for today. We will again meet tomorrow. Okay. So,
Okay, ma'am. Good night, ma'am.
good night. Good night, everyone.